Every time my friend talking about quantum physics, there's a guy like, quantum physics is so easy. I was like, so today we're gonna do other stuff then. So, what is black body radiation? A black body is an idealized physical body that absorbs all incident electromagnetic radiation regardless of frequency or angle of incidence. Hold on a second. So what the hell is electromagnetic radiation? So, electromagnetic radiation is a form of energy having wave-like properties that consist of rapidly varying electric and magnetic field. Now we're back to topic. So is every black body is actually black? Like black hole? Wait me 1 second. There we go. Okay. Black hole, coal, black cat, even black diamond though. Nope. Actually, yes and no. It doesn't really have to be black. I mean, don't have to be black. What the f? For normal objects, certain part of the light is always absorbed and the rest is reflected. For example, like the green leaf absorbs almost all the wavelength except of the green wavelength range between 500 nanomet and 550 nanomet. The reflected light contains exactly the wavelength range that gives us the green color impression. So, what is the example of black body object? Chill, I haven't done yet. So, as I said before, black body can absorb all the electromagnetic radiation. Okay, let's take example for the sun. Although it's also absorbed all of the radiation, but it's also created its own radiation. It's called solar radiation. It's the energy emitted by the sun, which is sent in all through direction through space as electromagnetic wave. The reason why the sun is not black because of the temperature variation on the surface and below, and because of absorption and emission of energy by many chemical continents. In other way, the temperature on the surface of the sun is about 5800 Kelvin. The radiation from a black body at this temperature is almost similar to that from the sun. So just quick reminder, 0 Kelvin is negative 273.15 Celsius. So 5800 Kelvin is around 5526.85 Celsius. 4 times hotter than lava. So here the black body curve, as you can see, the red one is shows the temperature of the lava, and then moving to left, you're getting hotter, and because it's getting hotter, the color change, like from red to orange, and then start to get yellow and white. And as you can see, like somebody can see, like at 5000 Kelvin, it's a little bit green here. It's almost the color of the sun. You keep moving to the star Sirius. Around 10,000 Kelvin is the temperature of Sirius star. So why does the sun isn't green? So I will explain it later in the video, so hold tight. How can we measure the electromagnetic energy of the black body object? That leads us to Stefan Boltzmann law. Quick introduction here. Joseph Stefan was born in 1835 and passed 1893. Ludwig Boltzmann, born in 1844 and passed 1906. And they will both create the equation for the black body curve. The Stefan Boltzmann law used to measure the power of electromagnetic radiation of an object. But we're talking about black body, so we use black body object right now. They can have like a more fancy word for power, they call like luminosity. Basically, to understand, it's like measure the temperature of that black body object or the surface area temperature of that black body object. So based on the equation of Stefan Boltzmann law, it's tell like the luminosity proportional with the area of that black body object and the temperature of that object to the power of 4. So there's a Stefan Boltzmann constant, which is 5.67 times 10 to the power of negative 8. So the symbol code is sigma, and the temperature we measure in Kelvin, which is the surface temperature of that black body object. Because of the Stefan Boltzmann equation, we have the famous graph here called the black body or black spectrum curve. On the y-axis we have the intensity, and the x-axis we have the wavelength. And look at this graph, it has 4 different curves. It shows The lowest curve show 2000 Kelvin and the highest curve have 5000 Kelvins, which is like the changing in temperature. So based on the of the scientists, they have the curve like this on the graph. Now we see the top of the curve, right? How they calculate it, we have to jump to Wind's law. The Wind's law is the equation. This law is known as the wind displacement law, which is the wind constant divided by T. The wind constant is 2.898 multiplied by 10 over -3 mK, meters Kelvin. This law is just only applied for black body object. So when you're done calculating, you get a curve, the top curve of in the graph. That is the color that the black object show when it have the amount of temperature. But based on our eyes, mostly we cannot see the exact color that we calculate out, because our eyes is not involved to distinguish to the color have low intensity with the high intensity, which is when it combine the color together, you cannot really see the color with high intensity. Now we go to Rayleigh-Jeans laws, which raised the huge problem in 1905. In 1905, Lord Rayleigh and James Jeans again tried to explain this curve with new approach. On C, which is the speed of light, constant K value, which is 1.38 multiplied by 10 to the power of -23. Unit of it is meters square, kilograms per second square per Kelvin. So look in the second graph here. So the graph have a curve, which is the one that all the scientists measurement out, and the cutting line here, which is Rayleigh-Jeans law based on the equation. And the graph turned out was wrong. It's not true on the reality, and then this is called the ultraviolet catastrophe because the physics broke down, turned with the experimental evidence. This was a real problem in the latter half of 19th century. And the equation just only true for half of the infrared wavelength. It starts to getting broke down when approaching the visible wavelength and the ultraviolet. So we go to Max Planck, who's the one to guess of Rayleigh-Jeans laws. His thinking is different. He thinks that Rayleigh-Jeans law make everything too complicated and it's garbage. He's not worried about that. He tried to prove the curve in a different way. So Max Planck was worried about the wind's displacement. After trying to prove everything, energy of the photon emitted by a black body or absorbed is equal to Planck constant times frequency. So to be easier, the reason Max Planck solved black body radiation is he treated the energy as a discrete quantity, and he come up with this equation, which fit perfectly with the black body curve graph. There are some careers that related to quantum mechanics. For example, lab manager, they ensure the technical working at their work, organize workflow, hire and train new staff. Data scientists gather and analyze large group of data. They in the quantum field may work with the machine learning and develop algorithm of quantum computer. Ethical engineer develop, analyze, then test these technologies, often working in fields such as aerospace, agriculture, and healthcare.